All right, guys, ready for this? This is really cool. I'm going to try this the simple way. And um, what I'm going to do is derive E equals gamma mc squared. This is the correct or most accurate expression for the energy of a massive particle. Um, great. And we do know that gamma is this, right? So what is this? Where does it come from? What does it show us? So this comes from the Lagrangian. Well, it comes from many different things. You could do like a relativistic collision where you have like, two balls colliding, at different speeds that are near the speed of light. And when they, mo like move away from each other, energy and momentum have to be conserved. But if you shift reference frames, right? Say you are in the reference frame where the right one isn't moving, right? These end up being the same, but the thing is you can't just add velocities like this. You have to do the relativistic version. And if you do that, you end up getting that the energy is this and the momentum is this. And if you do, then energy and momentum are conserved. But what's that assuming? That's assuming energy and momentum are conserved. So why don't we just, instead of choosing an example of collisions, which isn't, general, that's just like, okay, in collisions, this must be true. Let's do it generally. So in general, where does this come from? This comes from Noether's theorem and the Lagrangian, right? Specifically that, right? If L is invariant in time, which it is, then dl dt dot is constant. This is huge. This is the source of energy. And this constant we call energy. This is also called P sub T. It's like a generalized momentum. And I don't know where that, I mean, I kind of know obviously where that word, historically, as these theorems were developed came. It's just a word to mean that which is constant under time, under symmetry. P sub T is that which is constant under time symmetry, and that's called energy. So let's derive it. How do we do this? Well, we need a Lagrangian, right? Which I hopefully can explain where this comes from, but let's just accept that this is the Lagrangian. When given a metric, we have an xi dot is dxi d tau. Right? That's what the dot is. Xi, once again, I is time, R, theta, or phi, which is otherwise 0, 1, otherwise known as 0, 1, 2, or 3. Right? We're good, right? Cool. So, and this is a sum. And in the Lagrange video, I wrote this out for the whole thing, but that was for Schwarzschild. Let's do flat spacetime, because this is actually only for flat spacetime. This is special relativity. So what we do is for flat space-time, recall the metric is this. I'm going to do spherical coordinates, although we could easily do any other coordinate, but I'm just going to do this. Great. So this is GTT or G00, right? So obviously this is time invariant. It's not R invariant and it's not theta invariant, but it is invariant in time and invariant in phi. But for the time one, the time symmetry, right? Meaning if I take time and I add some constant, right, we get the same thing. right? This is a symmetry based on an invariant quantity called time, right? From that comes a constant we call PT, which is defined as dl dt dot from the Euler-Lagrange equation, right? Which we will define as energy. So what is it? So what we need to do is say, okay, um, great. So in terms of the Lagrangian here, well, that's going to be dl, sorry, the the only thing that has t dot in it, right, is sorry, I just got confused. Yeah, the only term that has t dot in it, so the t term of the Lagrangian is this, is m over 2 gtt times t dot squared. And if you look at the previous page, pause and let this make 100% sense from this, right? This leads to this in terms of just the t term. So if I plug in t, I get this, right? Great. I is t, j is t, or 0. Great, but gtt is what? That's c squared. So this is 1 half mc squared t dot squared, right? And this dl, right, dt, right, is this. What's that going to be? Well, that's going to be 2 times a half mc squared t dot. So that's going to be mc squared t dot. Easy, easy done, right? So we're pretty much done. Because if you remember, t dot is dt d tau, right? Which is gamma. Because remember, d tau, and by the way, the way I always remember this is that for light, right, tau goes to 0. That light experiences no time. Faster, less time. If you forget which order these go in, right? Tau is the observer, sorry, is the proper time. When I mean the observer, I meant the local moving observer, not the outside observer, right? And for light, it goes to 0. Moving things tick slower. So gamma, right, goes to infinity, which means dt goes to infinity as uh, as things move faster, which is another way of saying tau goes to 0. The point is this is gamma, which means our PT, which is energy, which is this, is gamma mc squared. This is an invariant quantity. This is the true invariant quantity of flat spacetime due to time symmetry. Isn't that gorgeous? And notice how it just comes from the metric. So the metric gives us this invariant quantity from the Lagrangian. And again, we can talk about where the Lagrangian comes from. But if we assume that to be true, if we take that to be true, we just follow it and we get this equation. Isn't that gorgeous? From this, we can derive. Now, this I didn't plan, so I'm going to try to do it by scratch, right? How do we do this? So right, dE equals F dx, which is force times delta x. Force is change in momentum over change in time dx. So and dx dt is velocity. With not r dot, but just proper velocity, right? I guess we call that vx in the x direction. So it's dp just times your velocity from an outside observer. Right? Does that kind of make sense? Right. So what we can do is say, okay, um, from this, and honestly, I'm not sure if I want to do this. If you have d gamma mc squared equals dpv, And you notice that this gamma is 1 over the square root of 1 minus v squared over c squared. Maybe pause and see if you guys can do this. I don't know if I have the space time right now. I'm hoping to at some point, but pause if you want to do this. Differentiate this. Take the differential of this. It's a constant. That's a constant, but v is your variable. Move this v over and then integrate both sides. So you get the integral of dp equals the integral of some expression dv, right? You're going to move that over. You're going to divide v over. You're going to differentiate first. So 1, do d of gamma mc squared. 2, divide by v on both sides to move that over. And 3, integrate. And you're going to get that p equals gamma mv. Yeah, cool. Now that's a little bit of algebra, a little bit of calculus there, kind of fun algebra and calculus, but you get that. So you get that E equals gamma mc squared, which is going to be E equals mc squared when something's not moving. So we call it the rest energy, and we call this the rest mass, right? So anything just sitting there, right? If I plug in V equals 0, gamma equals 1, right? So something has energy just being there. And we can talk about the theoretical origin of that, but Einstein figured out that anything just has inherent energy, E equals mc squared. The real equation, though, is E equals gamma mc squared, which means that gamma mc squared equals your rest mass plus your kinetic energy, plus your energy of motion, right? So this is mass energy plus energy of motion. We're not taking into account potential energy. This is just a particle, a free particle, no potential energy, no forces. Notice we didn't have any forces in our Lagrangian. We just had the metric, flat space-time metric, just from special relativity, flat space-time. Just your normal relativity, no funny stuff, no potential energy, right? E equals gamma mc squared. So that means kinetic energy, the real formula for that is gamma minus 1 mc squared. And then the low level limit, you can do a Taylor expansion of this, and you get that equals 1/2 mv squared. You get the Newtonian limit from that, which is kind of fun. I'll leave that as an exercise for you to do on your own if you wish. But it's kind of fun to show that this equals 1/2 mv squared at low velocities. That's kind of cool, right? I thought you'd like that. So if you have this, right? Our equation 1 and our equation 2, you can show they satisfy this relation. Again, I'll leave it as an exercise for you to plug this in here, to plug energy in here, right? And this is called the energy momentum relation. This is now how energy and momentum relate, as opposed to the classical, right? The classical was that. This is the more correct version that takes into account the rest mass energy. We have just done it. I hope that made more than 0 sense. So cool.